see how should we handle this particular message here, right? I'll use probably another color, right? So this should come here and get delivered here. When I'm showing this arrow, you can show even here, you can show even here, wherever you want, but it should be definitely after this particular event. So now let us see, the message that is coming here is coming with 001, right? Do the same thing again. It is 3 sending to 1. So look into the third index, 1, 1 minus 1 equal to 0. And as we did not deliver this here, so clock still remains same, 000 up to this particular point. So clock is still 000 because there was no updation that happened to P1's clock. Okay, so now this 000 is the still clock. Mr. Thiru is again asking, please explain the second condition. No, I am explaining again the second condition here when we talk about this particular example. So please bear with me till I complete the whole example. Maybe the second condition I am explaining 3rd or 4th times. Okay, so again it will be repeated when I talk about this particular receipt. So now when we see this 1 minus 1 equal to 0 and the third value is also 0, right? So there is no problem when it comes to first condition. Now look into second condition. Look into the remaining two values. Here it is 00 and what is here? Here also 00. So this 00 is greater than equal to this 00. That is true, right? Simply vector comparison. Now as condition 2 is also true, this can be delivered here. Now when we are delivering, we will do a maximization of the timestamp that is coming 001 and the vector value of the receiving side 000 because it has not yet been incremented. So the maximization of these two vectors max is 001. All of you will agree? This is a clock value. Now we will see, are we able to deliver this, which is also coming with a timestamp 011. Yeah. Sastikal asks, receiving should be greater than sender, right? This is condition 2. That is VT PJ, I am writing that equation, whatever was there, K should be greater than equal to VTMK. Okay, so this is the condition that we are doing. PJ is the receiving side, VTM is the timestamp in the message, and K is the index with all the values except the sender's index. That is K equal to 1 to N minus I. Right? So now if you see this particular message, it is 2 sending to 1. So we will look into this middle value 1 minus 1 equal to 0. And we have 0 here in the middle. The remaining two values of the clock 0 and 1 are greater than equal to this 0 and 1. And hence it can be delivered here. When you deliver, simply update it with a maximizing value 0, 1, 1. Right? So we solved now two examples. So it is greater than equal to, okay? There is equal to sign there. You can see this greater than equal to I am talking. Okay. Now with this we will solve a more complex problem. I'll take again another example of this BSS before we go to the next protocol. Okay. Yeah, so Mr. Somasekhar asks, don't we apply IR1 after computing the max in this case? No, we don't apply IR1. Okay, that's how the protocol is, because it's of no relevance when it comes to finding out the causal order violations. So I would request you all to take this local event as an example. I am taking a more complex one. Mr. Vasant has a question. Can you take local event as one example? So you solve it, and if you find difficulty, then you can ask me, right? I will take a more bigger or a more complex example with a non-broadcast communication and then converting into a broadcast, then applying BSS. Otherwise, BSS will fail. Right? So let us take that. Site 1, Site 2, Site 3. three sides. P1, let me name those. P1, P2, P3, right? If you would have attended the last session, we had this diagram, but we did not solve it. We simply tried to understand how the causal order is violated. Now we are applying BSS to solve the same example. So given a time space diagram like this, where your x-axis is the global time and y-axis is the space, let me number, okay, so these are three sends are there. 2 sends from P1 and 1 send from P2. Now if you see this diagram and you want to directly apply BSS to solve this problem, you will not be able to do, because this communication is not being shown as a broadcast communication. So your first task is to convert this into a broadcast communication and then apply BSS into this. So let me just convert this into a broadcast communication. Now I am adding other colored messages just for our understanding, but these are all the same message which you are broadcasting. So this is, I will say that probably right. So now I made this message as a broadcast. The second one has not gone to P3, so I'm making that one here, right? And the third one, I'm making it to P1 here. So by adding 3 arrows, all these red color arrows, I made this communication as a completely broadcast communication. So this is one send here, this is another send, and the first send is here happening. Now you can apply BSS protocol into this. So Mr. Senthil asks, is there any rules for making simple to broadcast? So there is no such rule. When I drew these arrows, you can draw wherever you want, right? Because your requirement to apply BSS is to have a broadcast communication in place. So if you say some messages will not reach or they are failing, then it's not a broadcast communication that you are experiencing, and protocol, BSS protocol cannot be applied there. Okay. Right, now let us solve this and see which message is to be deferred and which message is to be delivered. Okay, to ensure our causal order is maintained. So I will now start giving the clock values. First one, again I have 3 values, value 1, value 2, value 3. The first value is for P1, second value is for P2, and third value is for P3. That's how I am representing. So I'll give now the clock value as 1, 0, 0. The first index I am incrementing to 1. Right? The second is also a broadcast, so directly without worrying much, I can give this also as 2, 0, 0. The local index I am incrementing. Right? Now let us see what will happen to this receipt. Can we deliver this? Answer is yes. This is P1 sending to 2, so look into this. So 1 minus 1 equal to 0, and you have everything 0, 0, 0 here initially, all clock values. Right? So both the conditions are true. I will now give a clock value of 1, 0, 0 here. Now let us look into this particular message, this 2, 0, 0. So then it is 1 is sending to 2. So this 2 minus 1 equal to 1. And I will check what is the value here. This has already become 1. So first condition is true. Second condition says remaining 2 values, this 0, 0, is greater than or equal to this 0, 0. Hence this also can be delivered. So I am delivering this and doing a maximum of 2, 0, 0 and 1, 0, 0. So I'll get the clock value updated as 2, 0, 0. So as far as these 2 messages are concerned, one is this, other one is this, you don't have any problem. You got those 2 being delivered to P2, and you also got their clock values updated as 1, 0, 0, and then next time it is 2, 0, 0. Now if you see this line, these are all actually over crossing, like messages coming from P1, messages coming from both the messages. So we have now another real event which is happening here, that is the message send. So whenever there is a broadcast, we will increase its own index. So now the own index means it is P2 sending. So middle value should be incremented first. So when we are incrementing middle value, this 0 we are incrementing. Okay. Then first value will bring in, that is 2, and third value also will remain as it is. So the clock value of this particular broadcast is 210. That's how we have learned the algorithm in our vector clocks. Now we will see this timestamp that is going with this is 210. Let us see, can we deliver this here or not? So 2 is sending to 1. Look into the middle value, 1. So 1 minus 1 equal to 0, and you have middle value already 0 here. So first condition is met. Second condition says take these two values. I'll change the color here. These remaining two values, this 2 and this 0, first and third index. And these two values are greater than or equal to these two values, 2 and 0, in the timestamp. Hence, this can be delivered. When we are delivering this, we will simply apply maximum. So it is 210. Okay, that is max of the timestamp that is coming 210 and 200. So it is vector comparison. So max of 22, max of 10, max of 00. So this will be give you 210 as the value. Now the real problem will come, wherein we will see that what to do at P3. So we have one message here, one here, and one here. So we'll start from the left. So now this particular message is coming with a timestamp 210. Mr. Srikar asks, sir, why did not we consider the second message from P1 to P3? P1 to P3 at 100 before 210. No. So when we send this is the value, right? 200 that we gave. So this message is coming to P3. Now you may say that instead of landing this red here, you can come up to this, you can go up to that, you can do all that, right? So I did not say that when we convert a non-broadcast communication to a broadcast communication, where should we bring those arrows? Depending on where you are bringing, your values will change and your causal ordering will also differ. Okay. So with that, let us now see this value that is coming is 210. Now can we deliver here at this place? Now your answer should be, look into who is sending to whom. P2 is sending to 3. So look into the middle value. This is 1. Now that 1 minus 1 is 0. And look into the middle value of P3. Here just before this, the clock values are all zeros. So now the middle value is 0. So you compare this 0 with what you got here, 0. So condition 1 is true. Now the remaining two values, this 0 and 0, are not greater than equal to this 20. This is a more heavier value than the current clock value at P3. So hence this cannot be delivered. So I'll simply put it B. B means buffer. Okay. Now let us see what we'll do with this one. This is coming with a value 200. Right? The original clock value that has been given at the sending side. So now it is 1 sending to 3. Look into the first index, 2. 2 minus 1 equal to 1. Right? And this 1 is not equivalent to the 0 that is there in the first position at P3. So hence the condition 1 itself is failing here in this case. Although condition 2 is true, 00 is greater than or equal to 00. So any of the conditions is not fulfilled or met, then you cannot deliver the message. So this is also to be buffered. So I am writing 2 B's here in the P3. Now let us see what will happen to this third one. Here you can see it is coming with a clock value of 100, right? Now it is 1 sending to 3. So we will go to the first index 1 and 1 minus 1 equal to 0. So this 0 is equivalent to still the same clock value, because here also your clock value is 000, because we have buffered the previous two messages and we have not incremented the clock value of P3. So first value is also 0 here. So condition 1 is met. Condition 2 says 00 is greater than or equal to 00. Remaining two values at the receiving side and remaining two values at the timestamp. So this can be delivered. When we are delivering, we will increment it to 100. Now you may ask a question that should we deliver this next or this? Right? Should we deliver this message or this message? Because we buffered these two. We should deliver actually this one. Right? So the next thing that we'll do is we are delivering here. This is coming with 200. Now you can check all the conditions are met for this. 2 minus 1 equal to 1, and you have already got a 1 here. And condition 2 is also met. Z00 is greater than or equal to Z00. Then you can deliver this message. So when I am delivering this message, it is going like this and ending up here. Like it is coming with 210. So now 210, it is 2 sending to 3. So 1, this 1 minus 1 equal to 0, and you have, so now you have to also increment the clock. It will be 200 here. So you can see that this middle value 1 here in this minus 1 is there here, 0. 1 minus 1 equal to 0. Remaining two values are greater than or equal to 20 here. Since this can be delivered and the clock value is 210. So with this, we are now ending the BSS protocol, and I took sufficiently 3 different examples to ensure that there is a causal order violation in the original one, and we are changing it to or we are buffering and then making the right thing happening after applying the protocol. I'll now take 1 or 2 questions and then we'll go to the next protocol. Right, that is Schiffer-Egli-Sandoz, ACS. Yeah. How frequently, Mr. Prathanes asks one question. How frequently does a process check if it can deliver the earlier buffered message? So this is not again a significant question for us. When you say there is a multicast communication going on and you have got a message which you cannot deliver now, right? And subsequently to that, you are getting 3-4 messages, right? But all those are again giving you the same behavior, that is, you cannot deliver all those. So probably you can decide a period and then do this checking, right? So that maybe after next 5 minutes or 10 minutes, you will get the right message which has come up, and then you can deliver all the previously recorded or stored buffered messages. So that part is not of any significance, and it can vary from implementer to implementer. Sasikala asks, is there any particular order for checking the messages between processes? No, but we should go in the x-axis from left to right, because that is how we assumed that this is a linearly increasing order when it comes to the global time axis. So we should check with that. Don't start with, let's say, a message which is being seen at the right end of the x-axis or the time space diagram, leaving 3 to 4 messages which have been already arrived in the same line. Okay. So now with this, I will now go to the next protocol, ACS, and we will see there 1 or 2 examples also. Again, here you have 3 people who proposed their protocol: Schiffer, Egli, and Sandoz, ACS. Now, this ACS protocol does not require, or it does not mandate that your communication should be broadcast. So that you can see this is no need for broadcast messages. You can, if you have a unicast message, you need not convert into a broadcast and then apply this protocol, right? You can go through these steps. I will take examples, but I will just summarize what is the crux of this particular protocol. whenever there is a message sent that happens from one process to another process, there is a clock value that has to be accompanied or piggybacked in the message itself. Now, once you do that, there is a local vector which has to be updated with this information that has gone out from this particular site to the other one. Basically, there is a message which has gone, and what was the clock value that was there with this. So this is there is a tuple. So this tuple should be inserted into the vector, so that any further message that goes from this particular process to any other site in the time space diagram, whether to the same receiver to whom the earlier sent was done, or to another receiver which was not the previous receiver, this vector also has to reach, or vector also has to be sent along with the message having the timestamp and vector. Now the real thing comes is a process which is receiving this message will receive a message with a clock value and these vector values also. So the site which is receiving this message, if it sees a tuple with its own ID in the vector that is accompanied in the message, it will now check or compare its own clock with the clock that is there in the tuple. If the clock that is there in the tuple is more than the clock of the receiving site, then the message cannot be delivered. Message has to be buffered. Otherwise, message can be delivered. Now, once a message is delivered, whatever is there in the vector, that has to be merged into the local vector of the receiving site. And this is to be carried out for all the message sends and receives that are happening in the time space diagram. So this is what I explained, gave you a gist or a summary of these two slides, and you may go through these steps. I will directly apply this protocol to one or two examples. So before we go into this example, let me again take this simpler one, the way we started with the first one, the BSS protocol. Yeah, I got a message from Mr. Ravindra. Which reference material contain explanation for these protocols? Yeah, Sivaratri Singhal, the book has this, and of course your textbook also has references on these. Okay, so we will now take one example wherein the simplest one with two processes only, P1 and P2, and now we are applying ACS. So this is a message sent which is happening from P1 to P2, another message sent which is happening from P1 to P2 here. So here we will apply both IR1 and IR2 as per the vector clock. The way we did in the previous one, BSS, we will not be doing here. We have to increment the local value also in this. That's how the protocol is designed. So when you see that the other two, so here there is a causal, clearly there is a causal order violation. All of you will agree to this. Now I will give a clock value 10 after applying vector clock rule 1. Right? As I said, every process, every site here has a vector. So there is a VT, vector VT, maybe this is vector for P1. Similarly, you have a VT for process P2. This is P2 here. Right? Now we will see that, okay, this message that is coming. So first message that will come with the timestamp that we are giving, that is 10, and it will also come with an empty vector. Vector is empty here because nothing is there for the first message. Then immediately after that, let's say here, at this point in time, we will update this vector. So now vector will contain a tuple, two values consisting of this clock 10, right, and to whom the message has gone. The message has gone to P2. So this is what you will find in the tuple, a clock and the site to which this message has been sent. So this will be now the value of VTP1 at this point, right? Similarly, this will remain so till we reach to this particular send, right? Right, now let us see what will you do when we reach to this. We will again compute the clock value as per the vector clock. This will be 20. We are incrementing its own index first. This is 20. Now, when we send this message here to P2, we will use this vector clock value that has been computed, and also we will use the vector that has been updated prior to this particular message send. So I'll use now a different color. So it means this line that you are seeing will come with few things. Now those are, I'm writing here, it will come with a timestamp 20, and it will come with a tuple, this is a curly brace, with 10 and P2. This is only one entry will be there. So why I am saying tuple? Because in a complex case you will find more pairs like this. So this is what is there in the vector. So now this whole thing is coming in the message as a piggybacked message. So now let us see what will you do here. When there is a receipt which has to happen by P2, P2 first examines if there is a tuple with P2 as the name or ID. So here in our example, yes, it is there. Now as there is a tuple, it blindly cannot deliver this message. It has to now look into the clock in that tuple. Clock is 10, this is the timestamp that was given. And what is the current timestamp of P2 here just before the receipt? It is 00. So now a comparison emerges, or comparison has to happen, whether this 00 is greater than or equal to this 10 or not. Answer is no. So this is a more obsolete value or an old value than this. Hence, this particular message cannot be delivered. So you have to buffer it the way we did in BSS protocol. Cipher Egli Sandoz also says you have to buffer it. Now let us see what will you do with this particular message. If you see what was coming in this message was this much. A timestamp that is 10 and an empty vector, because that was the first message which was sent. So second message of P1 was carrying this information. That's how this part is there in the vector. Whereas in the first one it is empty vector. Now if there is no entry in the vector with P2 as the ID, the message can directly be delivered without doing any comparison. So with that logic, that is what the protocol says, one of the conditions. With that logic, you can deliver it. Now when you deliver, apply both IR1 and IR2 of the vector clock. So when we do that, we will see that the timestamp that is coming is 10, and here the clock value is still 00. So we'll do a max first, and then we'll apply the IR1 also. So this will be 1, 1, right? Maximum of 10 and 00 is 10, and then incrementing its own index, that is this 0, because it is P2. So we'll give a clock value of 1, 1, right? Now let us see, can we deliver the one which we delayed earlier? I'll use another color for that. So can we take this message from here, right, and then deliver it here? Let us do that. Again, the same process we have to repeat. We will simply now see that what is the tuple that is there in the vector. This is the tuple that is still there, and P2 is there. So we look into the clock. Clock is the timestamp is 10. You need to compare now that 10 and the clock value of the receiving process. It is 10. Sorry, this is 11. So this 11, the clock value of P2 is definitely greater than or equal to this. So this is a more recent value. This is an obsolete value. So now the timestamp in the vector tuple is an obsolete one, whereas for this particular case it was not so. The obsoleteness we were getting for the value that was there for P2. So in this case, as we have a good value for your receiving side, this can be delivered. So when we are delivering this, fine, we will apply both IR1 and IR2. So now the clock value that is coming is 20, the timestamp. So 20 and 11, maximum is 20 and 11. Max of these two vectors is 2 and 1, and then apply IR1 also. So increment this particular value. So this will be 2, 2. Right? So now this is the application of, this is 2 and 2. There is a vector clock at this side. This is the application of the Seyfert-Egli-Sandoz in this case. Mr. Kumar has a question. I did not get how 1, 1 came. Oh. So okay, 1, 1 is coming here because we are seeing the vector here. Now the vector has no entry with, yeah, I'll have to break the recording. Thank you, Mr. Sayan.